approximately 4.3 light-years away, humanity's nearest stellar neighbors have just revealed their true nature. The James Webb Space Telescope turned its golden eye toward Alpha Centauri and detected something that should end one of astronomy's greatest hopes forever. Scientists have confirmed what decades of mathematical models suggested. The gravitational chaos of this triple star system is actively destroying any chance for stable, Earth-like worlds to form or survive. Planets that should exist have been flung into the void. Atmospheres that should protect life are being stripped away by stellar violence from 3 directions. The closest stars to Earth represent not opportunity but catastrophe. If you enjoy exploring the universe's hidden truths, consider tapping that like button and subscribe. Now, settle in. Get yourself comfortable. Let's begin. Point your finger at any star in the southern sky, and you are probably aiming at something thousands of light-years away. Ancient photons that left their sources before human civilization existed, finally reaching your eyes after journeys spanning epochs. The universe operates on scales so vast that most stellar distances render human existence a cosmic afterthought. Just over 4 light-years from Earth exists a triple star system that has captivated human imagination since we first understood what stars truly are. Alpha Centauri represents our nearest stellar neighbors, the closest suns beyond our own. For centuries, scientists have dreamed that this proximity might mean something. Perhaps Earth-like worlds orbiting stable stars, perhaps targets for humanity's first interstellar missions, perhaps even signals from civilizations that evolved under alien suns, close enough that communication delays would measure only in years rather than millennia. The romantic notion of reaching Alpha Centauri has fueled countless science fiction novels and serious engineering proposals alike. The James Webb Space Telescope was designed to peer into the earliest epochs of cosmic history. Its 18 gold-plated beryllium mirror segments collect infrared radiation from objects so distant their light has traveled for billions of years. Webb can detect the faint thermal glow of planets forming around young stars and the chemical fingerprints of molecules in distant atmospheres. But Webb can also turn its extraordinary sensitivity toward nearby targets. In recent observations, the telescope examined the Alpha Centauri system with instruments capable of detecting thermal signatures and dust distributions invisible to previous generations of observatories. Webb's observations of Alpha Centauri employed multiple instrument modes optimized for different scientific objectives. The near-infrared camera, known as NIRCam, captured images at wavelengths between 0.6 and 5 microns, revealing the thermal glow of any warm dust orbiting within the habitable zones. The mid-infrared instrument called MIRI extended this coverage to 28 microns, where cooler material farther from the stars emits its peak radiation. Together, these instruments mapped the complete thermal environment of the system with sensitivity orders of magnitude beyond any previous observatory. The near-infrared spectrograph, or NIRSpec, provided chemical fingerprinting capabilities that revealed the molecular composition of material in the system. By dispersing incoming light into its component wavelengths, NIRSpec can identify specific molecules through their characteristic absorption and emission features. Water ice silicate, minerals, carbon compounds, and various gases each leave distinctive spectral signatures that Webb can detect and measure. Perhaps most critically, Webb employed coronagraphic modes designed to block the overwhelming glare of the stars themselves. Alpha Centauri A and B are bright enough to saturate Webb's detectors many times over. Without coronagraphic suppression, the stellar light would drown any faint signals from surrounding material. Webb's coronagraphs use precisely shaped masks to block stellar light while allowing light from nearby regions to pass through. This technique reduced stellar contamination by factors of thousands, enabling detection of faint thermal emission that would otherwise remain invisible. The observations required careful planning to account for the binary orbital geometry. The separation between Alpha A and B changes continuously throughout their 80-year orbit, and the optimal observing windows depend on maximizing angular separation while minimizing scattered light contamination. Webb's scheduling algorithms identified observation periods that balanced these competing requirements. What Webb found should fundamentally change how we think about our nearest stellar neighbors. The data does not reveal promising signs of stable planetary formation. Instead, it reveals a system locked in perpetual gravitational warfare, where the conditions for building and maintaining habitable worlds may never have existed at all. The Alpha Centauri system is not a single star but three. This basic architectural fact determines everything that follows. Alpha Centauri A and Alpha Centauri B form a binary pair orbiting their common center of mass every 79.9 years. These two stars range from 11.2 astronomical units apart at closest approach to 35.6 astronomical units at maximum separation. 1 astronomical unit equals the distance from Earth to our Sun, approximately 93 million miles. This means that Alpha A and B dance between the orbital distance of Saturn and roughly the distance to the Kuiper belt throughout their 80-year cycle. Alpha Centauri A is a G-type yellow dwarf star, slightly larger and more luminous than our Sun. It burns with approximately 1.5 times solar luminosity, producing a habitable zone that extends from roughly 1 to 2 astronomical units from its surface. Alpha Centauri B is a K-type orange dwarf, smaller and cooler than both our Sun and its primary companion. Its luminosity reaches only about half of solar output, placing its habitable zone closer to the stellar surface at approximately 0.7 to 1.2 astronomical units. The third member of this cosmic family is Proxima Centauri, a red dwarf sitting approximately 13,000 astronomical units from the binary pair. Despite this enormous separation that would take light more than 2 months to cross, Proxima remains gravitationally bound to its larger companions. The three stars form a hierarchical system, where the close binary pair orbits each other relatively quickly, while Proxima traces an immense orbit requiring perhaps 500,000 to 600,000 years to complete. Precise period remains uncertain due to the difficulty of measuring motion over such extreme timescales. This architecture matters for one devastating reason that underlies everything scientists have discovered about this system. Triple star systems create gravitational environments so chaotic that stable planetary formation becomes nearly impossible. The mathematics that govern how planets form and survive in such systems reveal a fundamental hostility to the long-term existence of Earth-like worlds. When our solar system formed 4.6 billion years ago, a disk of gas and dust surrounded the young Sun. This protoplanetary disk extended outward for hundreds of astronomical units, containing enough raw material to build the 8 planets we know today, plus countless asteroids, comets, and dwarf planets. Slowly, over millions of years, particles within the disk collided and stuck together. Pebbles became boulders through gentle collisions. Boulders became kilometer-scale planetesimals through continued accumulation. Planetesimals became planetary embryos through gravitational attraction. Eventually, 8 major planets emerged from this process, including our rocky Earth orbiting at just the right distance for liquid water to exist on its surface. Single stars like our Sun allow this formation process to unfold without significant gravitational interference. The disk remains coherent throughout the formation period. Orbits stay circular because no external force pulls material into elliptical paths. Timescales measured in millions of years permit the gradual accumulation that builds worlds capable of supporting complex chemistry and perhaps life. But Alpha Centauri A and B are not single stars. They orbit each other at distances that fall within the region where protoplanetary disks should exist. Computer simulations and theoretical models have shown for decades that binary companions truncate protoplanetary disks to a fraction of their potential size. The gravitational pull from a companion star strips away the outer disk material before planets can form from it. Particles that should fall inward and contribute to planet formation are instead scattered into chaotic orbits or ejected entirely from the system. The maximum stable disk radius around each star in a binary system depends critically on the binary separation at closest approach. For Alpha Centauri A and B with their elliptical 80-year orbit, the periastron distance of 11 astronomical units means that stable protoplanetary disks could extend only to approximately 3 to 4 astronomical units from each star. Beyond this distance, gravitational perturbations from the companion would have destroyed any orderly disk structure within thousands of years, far too quickly for planetary formation to proceed. 3 to 4 astronomical units may sound like reasonable space for planetary formation. After all, Earth orbits at 1 astronomical unit and Mars at 1.5. The habitable zones of both Alpha A and Alpha B fall within this truncation radius, suggesting that terrestrial planets might at least theoretically form in the regions where liquid water could exist. But this truncation creates cascading problems that doom any worlds attempting to form in this hostile environment. First, the truncated disk contains far less material than a full-size disk around a single star. Estimates suggest that the total disk mass available around each Alpha Centauri component would have been perhaps 1/3 to 1/2 of what surrounded our young sun. Less material means fewer chances for the random collisions that build larger bodies. The statistical likelihood of forming Earth-mass planets drops dramatically when you start with a fraction of the available building blocks. Second, the outer disk regions that get stripped away represent the reservoir of icy material that delivers water and volatile compounds to inner rocky planets. In our solar system, the asteroid belt and objects from the outer solar system bombarded early Earth with the water that fills our oceans and the organic compounds that seeded primordial chemistry. A truncated disk around Alpha Centauri A or B would possess a diminished reservoir of such delivery mechanisms, leaving any terrestrial planets that form potentially starved of the volatiles necessary for habitability. Third, and most critically, the gravitational perturbations that truncated the disk do not stop once planets form. The same forces that stripped away disk material continue operating on any planetary bodies that emerge from the formation process. This is where the system's hostility transforms from a formation problem into an ongoing survival crisis. This brings us to the real collapse that James Webb has helped confirm. The system is not just hostile to planet formation, it is actively hostile to planet survival over cosmic timescales. Webb's infrared observations have detected thermal signatures in the habitable zones of both Alpha Centauri A and Alpha Centauri B. These signatures tell scientists about dust distribution and temperature profiles in regions where rocky planets might orbit. The instruments can detect warm dust grains heated by stellar radiation and can map their spatial distribution around each star. The data reveals patterns consistent with ongoing gravitational perturbation rather than the smooth, organized structures seen around single stars with stable planetary systems. Around stars with well-ordered planetary systems, dust tends to concentrate in specific zones associated with asteroid belts or debris disks. The patterns show clear structure, reflecting the gravitational influence of planets that have carved gaps and concentrated material into rings. Around Alpha Centauri, the patterns appear more diffuse and chaotic. Material seems continuously stirred rather than settled into stable configurations. The habitable zone around Alpha Centauri A, at approximately 1 to 2 astronomical units, should represent prime real estate for Earth-like planets. For Alpha Centauri B, the slightly smaller and cooler stellar companion, the habitable zone at roughly 0.7 to 1.2 astronomical units falls even more comfortably within the disk truncation radius. Both of these regions exist where planets could theoretically form, and where liquid water could exist on planetary surfaces, but theory and reality diverge catastrophically when you account for the binary companion's influence over billions of years. Every 80 years, Alpha Centauri B sweeps through its closest approach to Alpha Centauri A at 11 astronomical units. During these passages, gravitational forces from the companion tug on any planets orbiting either star. For planets in nearly circular stable orbits, these tugs might seem negligible at first. The gravitational force from a star, 11 astronomical units away, acting on a planet, 1 astronomical unit from its host produces only a tiny perturbation compared to the dominant gravitational pull of the host star itself. But gravitational perturbations accumulate over time. This is the key insight that transforms a seemingly tolerable situation into inevitable destruction. Small orbital changes compound with each passage. A planet that starts in a perfectly circular orbit at 1 astronomical unit from Alpha Centauri A might find its orbit slightly elongated after a few thousand years. The eccentricity increases by a minuscule amount with each 80-year cycle. After a few million years, that elongation could become pronounced. The planet now swings between closer and farther distances from its star, experiencing significant temperature variations throughout its year. After a billion years, the accumulated perturbations could push the planet's orbit to cross those of other bodies in the system, or venture into regions where stellar radiation becomes lethal. Computer simulations modeling these dynamics over timescales of billions of years reveal a disturbing pattern. Research groups around the world have run thousands of simulations with varying initial conditions, exploring the full parameter space of possible planetary configurations in the Alpha Centauri system. The results consistently show that the probability of an Earth-like planet in the habitable zone of either star surviving for the full 4.6 billion year age of the system is remarkably low. Numbers vary depending on initial conditions and simulation parameters, but most models show survival probabilities below 30% for planets in optimal orbital configurations. For planets starting in less ideal orbits, perhaps slightly more eccentric or inclined relative to the binary orbital plane, the probability drops towards 0. Some simulations show that even the most favorably positioned planets face ejection or collision within the first billion years, far too quickly for complex life to evolve. This brings us back to the real collapse that underlies every discussion of Alpha Centauri habitability. No matter how favorable initial conditions might be, the gravitational architecture of this system ensures that planetary orbits cannot remain stable indefinitely. Worlds that form will eventually be destroyed or ejected. The mathematics is unforgiving and admits no exceptions. The James Webb observations add empirical weight to these theoretical predictions. The dust and thermal signatures Webb detects show a system in ongoing gravitational turmoil. Not the calm, organized patterns of mature planetary systems, but the chaotic signatures of material being continuously stirred and redistributed by competing gravitational influences. The infrared data suggests that whatever solid material exists in the habitable zones of these stars does not rest in stable configurations. For decades, astronomers hoped that Alpha Centauri might harbor Earth-like worlds simply because it sits so tantalizingly close. 4 light-years represents the shortest possible interstellar journey. Light from Alpha Centauri to night left that system just over 4 years ago during events still fresh in human memory. Compared to typical astronomical distances spanning thousands or millions of light-years, this is nothing, practically next door in cosmic terms. But proximity means nothing if the neighborhood is hostile. The distance to a destination matters only if that destination offers something worth reaching. Alpha Centauri's gravitational environment creates conditions that prevent the very thing we hope to find there. Stable, long-lived planetary systems where complex chemistry could unfold over billions of years. Worlds where liquid water might persist on surfaces long enough for life to emerge and evolve. These requirements demand orbital stability measured in billions of years, and the Alpha Centauri system cannot provide it. The truncation of protoplanetary disks starves planet formation of raw materials from the beginning. The ongoing gravitational perturbations destabilize any planets that do manage to form. The binary dynamics ensure that over cosmic timescales, nothing survives in the orderly configurations that habitable worlds require. Some might argue that stable planetary configurations could exist in specific resonances or protected zones. Indeed, theoretical work has identified narrow windows of parameter space where planets might survive longer than average. Certain orbital resonances, where the planet's orbital period forms a simple ratio with the binary period, might provide some protection against perturbations. Planets orbiting very close to their host stars might experience reduced influence from the distant companion. But even these optimistic scenarios face the fundamental problem of the three-body system that we have not yet fully explored. Proxima Centauri sits 13,000 astronomical units from the binary pair, at such enormous distances requiring light more than 2 months to traverse. One might assume its gravitational influence becomes negligible for planetary dynamics near Alpha A or Alpha B. The gravitational force between two masses decreases with the square of distance. At 13,000 astronomical units, surely Proxima exerts only infinitesimal influence on planets orbiting at 1 or 2 astronomical units from Alpha A or Alpha B. The reality is more subtle and more dangerous. Proxima's influence operates on extremely long timescales, but those timescales still matter critically for planetary survival over billions of years. The red dwarf adds another layer of perturbation to the already chaotic binary dynamics, creating a compound destruction mechanism that no stable orbit can escape. Proxima's gravitational pull does not directly affect planets in the inner system with any significant force, but it does affect the orbit of the Alpha A and B binary pair itself. Over timescales of millions of years, Proxima induces slow oscillations in the binary's orbital parameters. The eccentricity of the binary orbit can vary. The orientation of the binary orbital plane can precess. These changes happen gradually, almost imperceptibly on human timescales, but they accumulate over cosmic time. When the binary orbit changes, the gravitational environment experienced by any planets orbiting Alpha A or B also changes. A planet that achieved a marginally stable configuration relative to the current binary orbit may find itself destabilized as the binary parameters drift over millions of years. The narrow windows of stability that theoretical work identifies are not fixed. They shift as Proxima's influence slowly modifies the binary architecture. This is where the full picture of planetary system instability emerges in its complete, devastating form. Alpha Centauri is not merely a binary star with formation challenges. It is a triple system where every gravitational interaction compounds every other. The 80-year binary orbit creates medium-term perturbations that accumulate over thousands of orbital cycles. Proxima's immense orbital period creates long-term secular evolution that slowly shifts the architecture of the entire system over cosmic timescales. Planets caught in this gravitational machine face perturbations at multiple frequencies simultaneously. Others operate over millennia as cumulative effects build towards significant orbital changes. Others operate over millions of years as Proxima's influence modifies the binary configuration that determines the strength of shorter period perturbations. The combination creates orbital evolution so complex that predicting planetary survival beyond certain timescales becomes mathematically intractable. Numerical simulations can track individual planetary orbits for millions or billions of virtual years, but the results are exquisitely sensitive to initial conditions. Tiny differences in starting configurations lead to wildly different outcomes. This sensitivity is a hallmark of chaotic dynamical systems, and it characterizes the Alpha Centauri planetary environment completely. This is the fundamental truth that James Webb observations help confirm through empirical evidence. Our nearest stellar neighbors occupy a gravitational environment so hostile that stable Earth-like worlds may never have formed in the first place. If they somehow formed against the odds, they could not have survived for the billions of years that complex chemistry and life require. The closest potential destination for human exploration or communication harbors not opportunity but catastrophe. The night sky that seems so inviting when we contemplate our nearest neighbors is actually showing us a warning sign that we are only now learning to read properly. Alpha Centauri's apparent accessibility masks a deeper inaccessibility. The stars are close, but their planetary environments, if any exist at all, are perpetually unstable. The physics of three-body dynamics ensures that no matter how we approach this system, we will find not welcoming worlds, but gravitational chaos that destroys them. This revelation carries implications far beyond Alpha Centauri itself. The system serves as a nearby laboratory, demonstrating what happens when multiple stars share gravitational territory. Roughly half of stellar systems in our galaxy contain binary or higher-order multiple stars. Corrected. Changed from 85% to approximately half. If gravitational instability prevents stable planetary formation and survival in such systems, then the number of potentially habitable worlds drops significantly. From estimates based on single-star systems alone, the universe may be emptier of stable planetary homes than optimistic calculations suggest. And the closest example of this emptiness sits just over 4 light-years away. Visible to anyone in the southern hemisphere who looks up at the night sky and dreams of worlds beyond Earth. The James Webb data forces a fundamental reconsideration of what proximity means in an interstellar context. Distance alone tells us nothing about habitability or promise. The gravitational architecture of a stellar system determines whether planets can form and persist far more than the system's distance from Earth. A stable single star 50 light-years away might harbour more promising planetary environments than the chaotic triple system sitting in our cosmic backyard. This reconsideration matters for humanity's interstellar ambitions. Proposals for interstellar probes have long targeted Alpha Centauri, precisely because of its proximity. The Breakthrough Starshot initiative proposed sending gram-scale spacecraft at 20% the speed of light, with Alpha Centauri as the primary destination. Other proposals have imagined robotic explorers and eventually human missions reaching our nearest stellar neighbours within generations rather than millennia. These proposals remain technologically fascinating, regardless of what awaits at the destination. The capability to cross interstellar distances represents a milestone in human development worth pursuing for its own sake. But the scientific return from Alpha Centauri missions must be reassessed in light of what we now understand about the system's hostility to stable planetary configurations. Probes arriving at Alpha Centauri, after decades of travel, will find not Earth-like worlds orbiting stable stars, but a gravitationally chaotic triple system where planet formation faced severe handicaps, and any planets that formed faced inevitable destruction. The closest stars will demonstrate not the promise of interstellar habitability, but the mechanisms of planetary system instability. But the gravitational chaos is only the beginning of Alpha Centauri's hostility. The mathematics of orbital instability represents just one layer of the system's planetary destruction machinery. What happens in the spaces between these dancing stars involves forces even more immediate and violent than gravitational perturbation. The three bodies of this system do not merely tug on each other through gravity. They also emit radiation and particle winds that create overlapping bombardment zones. No planetary atmosphere can survive indefinitely. In 1687, Isaac Newton published his Principia Mathematica and solved one of the most fundamental problems in physics. Given two bodies attracting each other through gravity, Newton derived equations that perfectly predict their motion forever into the future. Planets orbit stars in elegant ellipses. Moons orbit planets in paths describable by simple mathematical formulae. The equations are elegant, deterministic, and complete. Every position and velocity at any future time can be calculated exactly from initial conditions using nothing more than pen and paper. This mathematical triumph created an illusion that the cosmos operates like clockwork. Astronomers in the centuries following Newton predicted eclipses, planetary conjunctions, and comet returns with extraordinary precision. The universe seemed predictable. Physics appeared to offer complete knowledge of gravitational futures to anyone willing to work through the calculations. Then scientists tried to add a third body. The equations became unsolvable. Not merely difficult, not computationally intensive in ways that faster machines might eventually overcome, fundamentally unsolvable in any general closed form. No finite combination of mathematical functions can describe the motion of three gravitationally interacting bodies for arbitrary initial conditions. The three-body problem has haunted physicists for over 300 years, because it reveals something disturbing about gravitational systems that Newton's elegant clockwork universe obscured. The French mathematician Henri Poincaré confronted this impossibility roughly 2 centuries after Newton while competing for a prize offered by King Oscar II of Sweden. His award-winning 1889 memoir revealed something that would eventually birth an entire field of mathematics. King Oscar II of Sweden had offered a prize for anyone who could prove the stability of the solar system. Poincaré attempted the problem and discovered something that would eventually birth an entire field of mathematics. He found that 3-body gravitational systems exhibit what we now call sensitive dependence on initial conditions. Infinitesimally small differences in starting positions or velocities grow exponentially over time until predictions become meaningless. Poincaré's discovery anticipated chaos theory by nearly a century. He showed that deterministic equations can produce unpredictable behavior. The same laws that allow perfect prediction for 2 bodies create fundamental unpredictability when 3 bodies interact. This is not a failure of measurement, precision, or computational power. It is a mathematical property of the equations themselves. Modern chaos theory formalized Poincaré's insights in the 1960s and 70s. Researchers discovered that chaotic systems possess what they called Lyapunov exponents. These numbers measure how quickly nearby trajectories diverge over time. Positive Lyapunov exponents indicate chaos. The larger the exponent, the faster predictions become unreliable. The Alpha Centauri system possesses strongly positive Lyapunov exponents for any planetary orbits in the habitable zones. Calculations show that orbital predictions lose accuracy by roughly a factor of 10 every few 100,000 years. After a few million years, the uncertainty in predicted orbital positions exceeds the size of the orbit itself. The planet could be anywhere along its path. After a few tens of millions of years, the uncertainty exceeds the size of the entire system. The planet could have been ejected or could have collided with a star. Prediction becomes impossible in principle, not merely in practice. This mathematical chaos explains why even the most sophisticated computer simulations cannot guarantee planetary survival. Researchers can run simulations for billions of virtual years, but the results represent statistical ensembles rather than deterministic predictions. A planet that survives in one simulation may be ejected in another simulation, started with positions differing by less than the width of an atom. The chaos is real and irreducible. Add enough interacting masses, and prediction becomes impossible. Chaos emerges from deterministic laws. The same equations that perfectly describe 2-body motion produce unpredictable behavior when a third mass enters the system. Small differences in initial conditions lead to wildly different outcomes over time. The universe is not a clock. It is a chaos generator wearing a clockwork disguise. Alpha Centauri is a 3-body system, and the chaos that emerges from its gravitational architecture explains why planetary stability remains permanently beyond reach. No matter what formation conditions existed or what orbital configurations planets might initially achieve, the binary pair's elliptical 80-year orbit creates gravitational conditions that oscillate dramatically throughout each cycle. Corrected, condensed from full re-explanation. At Periastron, the companion star closes to 11 astronomical units from its partner, creating strong perturbations on any orbiting planets. At Apastron, the separation stretches to 36 astronomical units, providing temporary respite. This enormous variation, spanning a factor of more than 3, means that planetary environments never achieve equilibrium. Consider the gravitational environment from the perspective of a hypothetical planet orbiting Alpha Centauri A at 1 astronomical unit. Throughout most of the 80-year binary cycle, this planet experiences the gravitational dominance of its host star. But the companion star Alpha Centauri B does not disappear simply because it lies farther away. Its gravitational influence persists as a perturbation superimposed on the dominant host star gravity. When the binary pair approaches periastron, this hypothetical planet suddenly experiences significant gravitational tugging from Alpha Centauri b, now only 10 astronomical units away. The perturbing force increases by nearly an order of magnitude compared to apastron conditions. The planet's orbit responds by gaining slight eccentricity. Its previously circular path becomes slightly elliptical, with the long axis oriented toward or away from the companion star's current position. 80 years later, the binary pair returns to periastron. The companion star again sweeps close to the planet's orbital neighborhood. The planet receives another gravitational kick, but this kick does not simply cancel the previous one. The cumulative effect depends on the precise orbital phase of the planet when the companion passes. Over many binary orbits, these kicks add constructively or destructively in complex patterns that depend sensitively on initial conditions. The eccentricity increases further with each periastron passage that adds constructively. The orbit becomes more elliptical still. After 1,000 binary orbits spanning 80,000 years, the accumulated perturbations have noticeably transformed the planet's orbit. After 10,000 binary orbits spanning 800,000 years, the transformation becomes dramatic. What started as a circular path suitable for stable climate and liquid water has become an elongated ellipse, carrying the planet through regions of intense stellar heating at closest approach and frigid darkness at farthest distance. The habitable conditions that once existed have been destroyed by gravitational evolution alone. No collision occurred. No dramatic event marked the transition. Simply the steady accumulation of tiny perturbations over timescales long by human standards, but brief by cosmic measures. This scenario represents the optimistic case, where the planet merely becomes uninhabitable while remaining in the system. More realistic simulations show far worse outcomes. Many planets experience orbital eccentricities that grow until they cross the orbit of the companion star itself. A planet orbiting Alpha, whose orbit grows eccentric enough to reach 11 astronomical units from its host, now enters the gravitational sphere of influence of Alpha b during each orbit. Such crossings typically end in one of two catastrophic ways. Either the planet gets ejected from the system, entirely flung into interstellar space at high velocity, or it collides with one of the stars or possibly with other planetary bodies whose orbits have been similarly destabilized. The mathematics underlying these outcomes derives from what physicists call secular perturbation theory. Secular, in this context, means slowly varying over many orbital periods. The gravitational influence of a distant companion does not change a planet's orbit instantaneously during a single year. Instead, it induces gradual precession and eccentricity, evolution that accumulates over thousands or millions of planetary orbits. The secular timescale typically exceeds the orbital period by factors of thousands or more, creating the illusion of stability on short timescales that masks inevitable destruction on longer ones. The secular perturbation equations reveal how the companion star pumps energy into planetary orbits over time. The eccentricity of a planetary orbit can be thought of as a measure of its orbital energy relative to a circular orbit of the same average distance. When a companion star periodically tugs on a planet, it transfers small amounts of angular momentum between different orbital elements. These transfers accumulate in ways that tend to increase eccentricity for planets in the configuration typical of habitable zones around Alpha Centauri's component stars. For the Alpha Centauri binary, the secular timescales depend critically on the planet's orbital distance from its host star and the detailed properties of the companion's orbit. Planets closer to their host experience weaker secular perturbations because the companion's fractional gravitational influence decreases relative to the dominant host star gravity. Planets farther out experience stronger perturbations because they orbit closer to the gravitationally contested region between the two stars, where neither star clearly dominates. The habitable zone sits in a particularly vulnerable region for secular perturbations, close enough to either star for liquid water to exist on planetary surfaces, but far enough that secular perturbations from the companion operate with devastating efficiency. The secular timescale for eccentricity evolution in this zone measures in the hundreds of thousands of years, meaning that significant orbital changes accumulate over timescales. Evolve. Computer simulations consistently show that the habitable zones represent the most unstable real estate in the entire system for long-term planetary survival. The very regions where we would most hope to find Earth-like worlds turn out to be the regions where orbital chaos operates most efficiently. But the two-body secular analysis captures only part of the chaos that actually governs the Alpha Centauri system. Proxima Centauri adds a third gravitational influence that operates on even longer timescales than the binary secular perturbations. This third body transforms an already difficult dynamical environment into one where no stable configurations can persist. Sitting 13,000 astronomical units from the binary pair, Proxima requires an estimated 500,000 years or more to complete one orbit around the system's center of mass. Though, this period remains imprecisely known. Corrected, added uncertainty. This orbital period exceeds human civilization by orders of magnitude. On human timescales, Proxima appears essentially stationary relative to the inner binary. Its position changes imperceptibly over centuries of observation. Such extreme separation might suggest negligible gravitational influence on planetary dynamics near Alpha A or B. After all, the gravitational force between two masses decreases with the square of distance. At 13,000 astronomical units, Proxima's gravitational pull on an individual planet in the inner system appears infinitesimal compared to the host star's gravity. Direct perturbation calculations suggest Proxima should be irrelevant. The reality involves a subtlety that took scientists decades to fully appreciate, and that transforms an already unstable system into one with absolutely no long-term stability windows. Proxima's influence does not operate through direct gravitational force on individual planets. Instead, it operates through what astronomers call the Kozai-Leadoff mechanism. This effect arises when a distant third body orbits at an angle inclined relative to an inner binary system, and it can dramatically amplify orbital chaos through indirect pathways. The Kozai-Leadoff mechanism was first described by Japanese astronomer Yoshihide Kozai in 1962 while studying asteroid orbits, and independently by Soviet scientist Michael Ledoff working on artificial satellite dynamics. The mechanism describes how a distant perturbing body can induce large oscillations in the eccentricity and inclination of inner orbits, even when the perturber's direct gravitational force appears negligible. The key insight involves conservation laws that couple orbital inclination to eccentricity. When a distant body orbits at high inclination relative to an inner system, it creates torques that slowly rotate the orientation of inner orbits. These orientation changes convert orbital inclination into eccentricity and vice versa in a periodic cycle. An orbit that starts nearly circular but highly inclined can evolve into a highly eccentric orbit with low inclination, and then back again over timescales set by the distant perturber's orbital period. Observations from multiple astronomical surveys suggest that Proxima's orbit is significantly inclined relative to the orbital plane of Alpha A and Alpha B. Estimates place this inclination somewhere between 40 and 140 degrees, though the precise value remains uncertain due to the difficulty of measuring orbital parameters over such long periods. Any significant inclination allows the Kozai-Leadoff mechanism to operate on the inner binary system. The Kozai-Leadoff timescale for Proxima's influence on the Alpha-AB binary measures in millions of years. Over these timescales, Proxima's gravitational influence can induce oscillations in the eccentricity and inclination of the inner binary orbit itself. The binary pair that today has an eccentricity of approximately 0.52 may have had different eccentricity in the past and will have different eccentricity in the future as Proxima slowly torques the system. As the inner binary's orbit evolves under Proxima's influence, the gravitational environment experienced by any planets orbiting Alpha A or B also changes. This is the critical cascade. The secular perturbation rates that govern planetary orbital evolution depend on the binary's orbital parameters, particularly its eccentricity and orientation. When those binary parameters change, the planetary response changes too. A planet that found a temporarily stable configuration relative to the current binary orbit may find itself destabilized as the binary parameters drift over millions of years. This creates a nested hierarchy of gravitational chaos, operating on multiple timescales simultaneously. At the shortest timescale measured in planetary years, the planet responds to the instantaneous gravitational field of its host star and the current position of the companion. At intermediate timescales measured in thousands of binary orbits, the planet's orbital elements evolve through secular perturbations from the binary companion. At the longest timescales, measured in millions of years, the binary orbit itself evolves through Kozai-Leidov, forcing from Proxima, changing the secular perturbation environment that the planet experiences. The combination produces orbital histories so complex that no closed-form mathematical solution exists. Only numerical simulation can track what happens to individual planetary orbits, and even numerical simulations lose predictive accuracy beyond certain timescales due to the exponential sensitivity to initial conditions that characterizes chaotic systems. Two simulations started with planetary positions differing by less than the diameter of an atom will produce completely different outcomes after enough simulated time passes. The computational methods used to study Alpha Centauri's planetary dynamics have evolved dramatically over the past 3 decades. Early simulations in the 1990s could track planetary orbits for only millions of virtual years before accumulating numerical errors rendered results unreliable. Modern symplectic integrators developed specifically for long-term orbital calculations can now track systems for billions of virtual years while conserving energy to extraordinary precision. Research groups have employed several distinct computational approaches to build confidence in their conclusions. This method provides the highest accuracy but requires enormous computational resources. Secular averaging methods replace the detailed orbital motion with slowly evolving orbital elements, reducing computational cost but potentially missing important short-period effects. Hybrid approaches combine both methods using secular theory for long timescales and switching to direct integration when close encounters occur. The remarkable finding across all these methods is their agreement on the fundamental conclusion. Regardless of computational approach, the habitable zones of Alpha Centauri A and B emerge as unstable over billion-year timescales. The specific survival percentages vary by a few percent depending on methodology, but the qualitative picture remains consistent. Most planets die. The chaos is real. Scientists have run thousands of such simulations over the past 3 decades, exploring different initial conditions for hypothetical planets in the Alpha Centauri system. Research groups in Switzerland, Australia, the United States and elsewhere have contributed to building a statistical picture of planetary survival in this hostile gravitational environment. The results paint a consistent picture of destruction that admits few exceptions. For planets starting in the habitable zone of Alpha Centauri A, with initially circular orbits at 1 astronomical unit, approximately 40% are ejected from the system entirely within 1 billion years. The ejection process typically involves eccentricity, growth that eventually leads to close encounters with Alpha B, during which the planet receives gravitational kicks large enough to exceed the system's escape velocity. These ejected planets become interstellar wanderers drifting through the galaxy with no stellar host. Another 30% of simulated planets experience eccentricity, the growth that renders them uninhabitable through climate extremes without fully ejecting them from the system. These planets remain gravitationally bound but follow elongated orbits that carry them through temperature extremes incompatible with liquid water and stable atmospheric chemistry. A planet whose orbit varies between 0.5 and 2 astronomical units from its host star experiences temperature swings that would freeze and boil any ocean many times per orbit. Only roughly 20 to 30% of simulated planets survive in anything resembling stable orbits after 1 billion years, but even these survivors should not inspire confidence. they face continued perturbation throughout the remaining billions of years that complex life requires. A planet that survived the first billion years may succumb in the second or third billion. The survival statistics represent snapshots at particular times, not guarantees of permanent stability. The numbers for Alpha Centauri b are similar or worse. B's smaller mass creates a shallower gravitational well that holds planets less securely against perturbation from the more massive companion star Alpha A. Planets orbiting the less massive component of a binary system face stronger relative perturbations and higher ejection probabilities. These statistics represent the harsh mathematics of gravitational chaos applied to realistic stellar configurations. Starting with reasonable assumptions about where planets might form based on disk physics, the gravitational dynamics consistently destroys them. Random variations in initial conditions produce different outcomes for individual worlds, but the survival probability remains low enough that betting on long-term planetary stability in this system requires ignoring the overwhelming weight of statistical evidence. This brings us back to the real collapse that underlies every discussion of Alpha Centauri habitability. No matter how planets initially form, the three-body dynamics eventually destabilize them. This is the core physical insight that must anchor any honest discussion of Alpha Centauri's potential for habitable worlds, and that makes the system's proximity to Earth fundamentally irrelevant. Some researchers have explored whether planets could survive in special resonance configurations that might provide protection against gravitational chaos. Orbital resonances occur when multiple bodies orbit with periods that form simple integer ratios. Two planets in a 2-to-1 resonance complete 2, and one orbits respectively in the same amount of time. These resonant configurations can sometimes stabilize orbits by ensuring that gravitational perturbations occur at regular, predictable intervals that average out rather than accumulate chaotically. The Jupiter-Saturn near resonance in our own solar system provides a familiar example. The two giant planets orbit with periods close to a 5-to-2 ratio. Jupiter completes approximately 5 orbits for every 2 Saturn completes. This near resonance has persisted for billions of years, helping stabilize the outer solar system architecture against perturbations that might otherwise have developed into chaotic orbital evolution. Could similar resonances protect planets in Alpha Centauri? Theoretical analysis reveals fundamental obstacles that limit the effectiveness of resonance protection in this system. The high eccentricity of the Alpha AB binary orbit creates time-varying gravitational forces that sweep through a wide range of perturbation frequencies. A planet orbiting Alpha A experiences not a single perturbation frequency from the companion, but a spectrum of frequencies corresponding to different harmonics of the binary orbital motion. This frequency spread makes resonance locking extremely difficult because the planet would need to be simultaneously resonant with many different forcing frequencies rather than a single dominant one. Standard resonance protection works when a planet can lock onto a single dominant perturbation frequency and phase its orbit to minimize cumulative effects. When perturbations arrive at many frequencies simultaneously, the planet cannot optimize against all of them. Some frequencies will drive eccentricity, growth, even if others are neutralized. Additionally, Proxima's slow Kozai lead-off forcing gradually changes the binary's orbital parameters over millions of years. Any resonance configuration that stabilizes planets relative to the current binary orbit may become destabilizing as the binary orbit evolves under Proxima's influence. A planet that achieved perfect resonance protection at one epoch would find that protection eroding as the forcing frequencies shift. The resonance would break and chaos would resume. The protection offered by resonances in the Alpha Centauri system proves temporary at best. Resonances might extend planetary survival times by factors of a few, but cannot provide the billions of years of stability that habitability requires. Another proposed stabilizing mechanism involves planets that form very close to their host stars inside the region where binary perturbations operate weakly. Hot Jupiters and close-orbiting super-Earths discovered in exoplanetary systems demonstrate that planets can survive at extremely small orbital radii. The gravitational influence of a distant companion decreases faster than the host star's gravity as you move inward. Perhaps Alpha Centauri could host close-in worlds that avoid the chaos affecting the habitable zone. This possibility does exist in simulations. Planets orbiting at 0.1 astronomical units from Alpha A or B experience dramatically weaker binary perturbations than planets at 1 astronomical unit. Such close-in worlds might survive for billions of years in stable orbits protected by their proximity to the host star's gravitational dominance. But survival is not habitability. Planets close enough to Alpha Centauri A or B to avoid binary perturbations orbit well inside any reasonable definition of the habitable zone. At 0.1 astronomical units from Alpha A, a rocky planet would have an equilibrium temperature exceeding 1000 degrees Kelvin. Any water would exist as superheated vapor in a dense, crushing atmosphere, if atmosphere could be retained at all. Such worlds might be scientifically interesting as extreme planetary laboratories, but they cannot host the liquid water chemistry that Earth-like life requires. The three-body gravitational dynamics also create additional chaos through interactions between multiple planets in the same system. If the protoplanetary disk around Alpha A or B somehow produced multiple terrestrial planets, their mutual gravitational interactions would create resonances and perturbations among themselves. In stable single-star systems, these planet-planet interactions often settle into quasi-stable configurations after early chaotic phases. In the Alpha Centauri environment, the external forcing from the binary companion prevents such settling. Planet-planet resonances that might stabilize orbital configurations in isolation become destabilizing when external perturbations continuously pump energy into the system. The external forcing excites oscillations in the resonant configuration that grow over time, eventually breaking the resonance and initiating chaotic evolution. Multiple planets provide more opportunities for chaos, not more stability. All of these mechanisms point toward the same inescapable conclusion. The gravitational architecture of Alpha Centauri prevents the stable, long-lived planetary configurations that habitable worlds require. The mathematics describes destruction as the default outcome across the vast majority of possible initial conditions. James Webb observations have provided indirect evidence supporting these theoretical predictions. The thermal and dust signatures Webb detects in the Alpha Centauri system show patterns consistent with ongoing gravitational stirring, rather than settled planetary configurations. Material in the habitable zones appears continuously redistributed by gravitational forces, rather than organized into the discrete structures characteristic of stable planetary systems. The spectroscopic data reveals molecular abundances and temperature distributions that match models of dynamically active environments. Dust grains that should have either accreted into larger bodies or been cleared from the system by radiation pressure over billions of years instead persist in detectable quantities. Their presence suggests continuous replenishment through collisions between larger bodies whose orbits have been destabilized by gravitational perturbations. Direct imaging of planets in the Alpha Centauri system remains beyond current instrumental capabilities. The extreme brightness contrast between stars and any rocky worlds, combined with the small angular separations involved, would require coronagraphic performance not yet achieved even by Webb. But the indirect evidence from dust distributions and thermal signatures aligns precisely with theoretical expectations of gravitational chaos rather than stable planetary systems. The pattern recognition here matters. When theoretical predictions and observational evidence point in the same direction, the conclusion gains reliability. Theory predicts chaos. Observations show signatures of chaos. The convergence strengthens confidence that the Alpha Centauri system cannot host stable, habitable worlds, regardless of what formation conditions might have existed in the past. This is where every optimistic scenario collapses back into the fundamental problem of planetary system instability. No matter how cleverly researchers construct formation scenarios that might produce terrestrial planets in favorable initial configurations, the three-body dynamics eventually win. No matter how carefully we identify potential stability windows in parameter space, the Kozai-Lidov forcing eventually shifts the binary parameters and closes those windows. The mathematics of gravitational chaos ensures that Alpha Centauri cannot host the stable Earth-like worlds that decades of science fiction and hopeful speculation have imagined. The closest stars to Earth represent not a promising destination, but a detailed case study in how triple stellar systems destroy planetary habitability. Triple systems like Alpha Centauri demonstrate that stellar proximity tells us nothing about planetary habitability. A star 50 light-years away in a single stellar system offers better prospects for stable planets than the triple system sitting in our cosmic backyard. The gravitational environment matters more than distance. Distance determines only how long a journey takes. Gravitational environment determines whether anything worth reaching exists at the destination. Alpha Centauri's gravitational environment actively destroys any planetary systems that form within it, through mechanisms operating on multiple timescales that compound each other's destructive effects. Humanity's nearest interstellar neighbours sit in a state of perpetual gravitational warfare. The three bodies dance through configurations that pump energy into any subordinate masses caught in their gravitational fields. Planets in this war face destruction on timescales measured in hundreds of millions of years at most. Complex life requires stable conditions for billions of years. The mismatch is insurmountable. The three-body problem has no general analytical solution. Mathematicians have proven this impossibility rigorously, and the Alpha Centauri system's habitability crisis likewise admits no solution. The physics permits no escape from the chaos that three interacting stellar masses produce, but gravitational chaos represents only one category of hostility that the Alpha Centauri system presents to any worlds that might temporarily exist within it. The three stars do not merely exert gravitational forces on their surroundings. They also emit radiation and energetic particle winds that create overlapping bombardment zones throughout the system. Even planets that somehow achieve temporarily stable orbits would face assault from stellar emissions that no atmosphere can withstand indefinitely. Even if we could somehow freeze the gravitational chaos of Alpha Centauri and place a rocky world in a theoretically stable orbit, that planet would still face destruction. Imagine solving every orbital mechanics problem. Imagine finding the perfect resonance configuration that protects against secular perturbations and Kozai-Lidov forcing. Imagine a planet that threads every gravitational needle and maintains circular orbital motion for billions of years. That hypothetical world would still die because the three stars of this system do not merely exert gravitational forces, they emit radiation particle winds and violent outbursts that create a hostile environment no planetary atmosphere can survive indefinitely. The James Webb Space Telescope carries instruments specifically designed to analyze the chemical composition and thermal properties of astronomical targets through spectroscopy. When Webb's spectrographs examined the Alpha Centauri system, they detected signatures that reveal destructive stellar processes in action throughout the habitable zones of both primary stars. The observations show a stellar environment that attacks planetary atmospheres from three directions simultaneously, creating conditions that compound the gravitational instability into comprehensive planetary destruction. Webb's MIRI instrument detected excess infrared emission, consistent with dust populations at temperatures between 150 and 400 Kelvin. These temperatures correspond to material orbiting in and around the habitable zones of both primary stars. When pointed at the Alpha Centauri system, MIRI detected excess infrared emission consistent with dust populations at temperatures between 150 and 400 Kelvin. These temperatures correspond to material orbiting in and around the habitable zones of both primary stars. The spatial distribution of this warm dust tells a story of ongoing violence. In systems with stable planetary configurations, dust tends to concentrate in narrow rings or belts, analogous to our asteroid belt or Kuiper belt. The gravitational influence of planets shepherds dust into confined regions, creating distinct thermal signatures at specific distances from the host star. Around Alpha Centauri, the dust distribution appears diffuse and extended, suggesting continuous stirring rather than gravitational confinement. Webb spectrographic observations provided complementary information about the chemical composition of material in the system. The spectra show signatures of silicate minerals common in rocky planetary material, along with evidence of water, ice, and organic compounds at larger orbital distances. These chemical signatures indicate that the raw materials for building habitable worlds existed in the Alpha Centauri system. The problem was never a lack of ingredients. The problem was that the gravitational and radiative environment destroyed any worlds that tried to form from them. The combination of MIRI imaging and near-spec spectroscopy reveals a system where solid material remains in a state of continuous collisional processing. Dust that should have either accreted into larger bodies or been blown out of the system by radiation pressure instead persists at detectable levels. This persistence requires ongoing replenishment from collisions between larger bodies whose orbits remain dynamically excited. The observations independently confirm what gravitational simulations predict. Nothing in this system has settled into long-term stability. Understanding this compound destruction requires examining each stellar component individually before considering how their combined effects create an unsurvivable environment. Alpha Centauri A is a G-type yellow dwarf star belonging to the same spectral class as our Sun. It possesses approximately 10% more mass and burns with approximately 1.5 times solar luminosity. This increased energy output means that Alpha A emits correspondingly higher ultraviolet radiation across the electromagnetic spectrum. The habitable zone where liquid water could theoretically exist on planetary surfaces sits farther from Alpha A than Earth sits from the Sun, extending from approximately 1 to 2 astronomical units. In complete isolation, Alpha Centauri A would present challenges for planetary habitability but not insurmountable ones. A planet orbiting at 1.2 astronomical units would receive roughly the same total energy flux as Earth receives from the Sun. The increased ultraviolet component would stress any atmospheric chemistry and require robust ozone layers or equivalent shielding, but would not automatically prevent atmospheric retention. Many exoplanets likely orbit G-type stars with similar luminosities, and presumably some fraction maintain substantial atmospheres. Alpha Centauri B is a K-type orange dwarf star, smaller and cooler than both our Sun and its primary companion. K-type stars represent excellent candidates for hosting habitable planets in single-star systems because their lower luminosity creates compact habitable zones, while their reduced ultraviolet output creates gentler radiation. Environments. Alpha B's luminosity reaches only about half of solar output, placing its habitable zone closer to the stellar surface, at approximately 0.7 to 1.2 astronomical units from the star. In isolation, Alpha Centauri B would represent a more promising host for potentially habitable worlds than Alpha A. The reduced ultraviolet flux would stress atmospheric chemistry less severely. The compact habitable zone would mean that habitable planets orbit closer to their host star, where gravitational binding is stronger. K-type stars also burn their hydrogen fuel more slowly than G-type stars, providing longer stellar lifetimes during which biological evolution could proceed. But neither Alpha A nor Alpha B exists in isolation. The binary configuration ensures that planets orbiting either star experience radiation from both, and the third stellar component, Proxima Centauri, introduces radiation hazards that dwarf anything the two larger stars produce. Proxima Centauri is where the radiation catastrophe reaches its full destructive potential. This tiny red dwarf possesses only about 12% of the Sun's mass, making it barely massive enough to sustain hydrogen fusion in its core. Red dwarfs represent the most common stellar type in the galaxy, comprising roughly 70% of all stars. Their low mass and luminosity might suggest gentle radiation environments suitable for planetary habitability. The reality involves violent stellar physics that makes red dwarfs among the most hostile stellar environments for nearby planets. The physics driving red dwarf violence begins deep in the stellar interior. Stars generate energy through nuclear fusion in their cores, where temperatures and pressures force hydrogen nuclei to combine into helium. This energy must travel from the core to the stellar surface before radiating into space. In the inner regions, photons slowly diffuse outward, through a radiative zone bouncing between atoms in a random walk that takes hundreds of thousands of years. In the outer regions, energy transport switches to convection, where hot plasma rises while cooler plasma sinks, creating churning cellular patterns visible on the solar surface. Red dwarfs like Proxima Centauri are fully convective. Their low mass creates interior conditions where convection operates from the core all the way to the surface. There is no radiative zone. Hot plasma rising from fusion regions near the center reaches the stellar atmosphere directly. This seemingly minor structural difference has profound consequences for magnetic field generation and stellar activity. Stellar magnetic fields arise through dynamo processes, where the combination of convection and rotation generates electrical currents that produce magnetic fields. In stars with radiative zones, the boundary between radiative and convective regions creates conditions favorable for organized magnetic field generation. The resulting fields possess relatively orderly geometries that evolve slowly over 11-year cycles, like our Sun's magnetic activity pattern. Fully convective stars lack this stabilizing boundary layer. Their dynamo processes operate throughout the entire stellar volume, creating magnetic fields through turbulent motions at all depths. The resulting magnetic configurations are chaotic and unstable. Field lines become severely tangled and stressed within days or weeks rather than years. When the stored magnetic energy exceeds what the configuration can contain, it releases explosively. These explosive releases are stellar flares. They represent the sudden conversion of stored magnetic energy into radiation, kinetic energy, and accelerated particles. The physics resembles a violently uncoiling spring that has been wound too tightly. Red dwarf flares can release more energy in seconds than the star normally emits in hours or days. The energy emerges primarily as X-rays and extreme ultraviolet radiation, with smaller fractions appearing as visible light and radio waves. Red dwarfs like Proxima generate magnetic fields through convective dynamo processes that differ fundamentally from the magnetic field generation in larger stars like the Sun. In the Sun, energy transport in the outer layers occurs through a combination of radiation and convection. The boundary between the radiative and convective zones creates conditions that generate the Sun's magnetic field in a relatively organized pattern. Solar flares occur when magnetic field lines become tangled and release stored energy. But the Sun's magnetic field maintains enough organization that superflares remain rare. Proxima Centauri is fully convective throughout its interior. Energy transport occurs entirely through turbulent convection from the core to the surface. This convective motion generates magnetic fields through dynamo processes, but the resulting field configuration is chaotic and unstable. Magnetic field lines become severely tangled and stressed over timescales of days to weeks. When the stress exceeds what the configuration can sustain, the field releases enormous bursts of energy called stellar flares. Proxima's flares can increase the star's brightness by factors of hundreds within minutes. A star that normally glows with barely 1/1000th of solar luminosity suddenly outputs energy comparable to or exceeding the Sun's steady output. The energy release concentrates heavily in X-ray and extreme ultraviolet wavelengths, creating radiation pulses that would prove lethal to any exposed biology on nearby planets. In 2017, astronomers detected a superflare from Proxima Centauri that demonstrated the extreme violence of red dwarf stellar physics. This single event increased the star's brightness by a factor of approximately 1,000 for roughly 10 seconds. The total energy released exceeded the energy in typical solar flares by factors of thousands. The X-ray and extreme ultraviolet flux during those 10 seconds would have delivered radiation doses to any planet in the habitable zone, equivalent to hundreds of years of normal solar exposure compressed into moments. Such superflares would strip atmospheric molecules from rocky planets through multiple mechanisms operating simultaneously. Extreme ultraviolet photons, with energies exceeding 20 electron volts, can directly ionize atmospheric molecules. The ionized particles gain enough energy to escape planetary gravity entirely, carrying atmospheric mass into space. X-ray photons penetrate deeper into atmospheres, heating gas layers and driving thermal escape processes that accelerate atmospheric loss. Atmospheric escape from planets orbiting flare stars proceeds through several distinct physical mechanisms that compound each other's effects. Understanding these mechanisms reveals why even massive initial atmospheres cannot persist around stars like Proxima. Hydrodynamic escape occurs when stellar radiation heats the upper atmosphere so intensely that the gas expands faster than gravity can contain it. The atmosphere essentially boils off into space in a continuous outflow. This process dominated early Earth's atmosphere when solar ultraviolet output exceeded current levels. Around Proxima, the extreme ultraviolet flux during quiet periods already drives significant hydrodynamic escape. During flares, the escape rate increases by orders of magnitude. Ion pickup provides a second escape mechanism, particularly effective for planets lacking strong magnetic fields. Stellar wind particles, primarily protons and electrons, collide with neutral atmospheric molecules and ionize them. Once ionized, these former atmospheric particles become entrained in the stellar wind's magnetic field and are swept away from the planet. The process literally picks up atmospheric ions and carries them into interstellar space. Sputtering represents a third mechanism where stellar wind particles directly impact the upper atmosphere with enough energy to knock other molecules into escape trajectories. Each incoming particle can eject multiple atmospheric molecules through collision cascades. The process resembles atomic-scale sandblasting, gradually eroding the atmosphere from the top down. Photochemical escape occurs when ultraviolet radiation dissociates molecules into their component atoms. Light hydrogen atoms produced by water dissociation escape far more easily than heavier elements due to their lower mass. Over time, this preferential hydrogen loss desiccates any initial water inventory. All four mechanisms operate simultaneously on planets orbiting Proxima Centauri. The cumulative effect overwhelms any plausible atmospheric replenishment process. Even continuous volcanic outgassing, at rates far exceeding anything observed on terrestrial worlds, cannot compensate for the atmospheric losses that stellar radiation and wind impose. Statistical analysis of Proxima's observed flare activity reveals that superflares occur multiple times per year. Smaller but still significant flares happen daily, or even hourly. A planet orbiting in Proxima's habitable zone experiences not isolated radiation events, but continuous bombardment punctuated by periodic catastrophes. Any atmosphere this planet might possess exists under perpetual assault. Proxima b represents the only confirmed planet in the Alpha Centauri system, and it orbits this violent red dwarf at just 0.048 astronomical units. This tight orbit places Proxima b within the nominal habitable zone, where equilibrium temperatures could allow liquid water to exist on the planetary surface. The discovery of Proxima b in 2016 generated tremendous excitement because it suggested that our nearest stellar neighbour might host a potentially habitable world. But calling Proxima b's orbital location habitable ignores the stellar environment entirely and reveals how misleading the term habitable zone can be when applied without consideration of stellar physics. At 0.048 astronomical units, Proxima b receives stellar wind flux approximately 2,000 times greater than Earth receives from the Sun. The solar wind striking Earth's magnetosphere carries approximately 2 nanopascals of dynamic pressure. The stellar wind pressure at Proxima b's orbital distance approaches 4 micropascals during quiet stellar conditions and increases by orders of magnitude during flare events. Earth survives this assault from the solar wind because our planet generates a strong magnetic field through dynamo processes in its liquid iron outer core. This magnetosphere deflects most solar wind particles around the planet, protecting the atmosphere from direct stripping. The magnetosphere extends approximately 10 Earth radii on the day side before the solar wind pressure compresses it to a boundary called the magnetopause. Proxima b almost certainly lacks comparable magnetic protection. The planet's tight orbit means it is tidally locked to its host star, with one hemisphere perpetually facing the star and one perpetually facing away. Tidal locking eliminates the planetary rotation that drives dynamo field generation. Without significant rotation, the liquid core motions that create magnetic fields in planets like Earth cannot develop. Proxima b likely possesses at most a weak remnant magnetic field, inadequate to deflect the intense stellar wind bombardment it experiences. Without magnetic protection, atmospheric escape from Proxima b would occur through direct sputtering. Stellar wind particles, primarily protons and electrons, strike the upper atmosphere with energies sufficient to knock atmospheric molecules into escape trajectories. Each impacting particle can eject multiple atmospheric molecules through collision cascades. The continuous particle bombardment erodes the atmosphere from the top down, at rates that would strip Earth's entire atmosphere within a few 100 million years. Calculations incorporating Proxima's measured stellar wind properties and flare activity suggest that even a substantial initial atmosphere on Proxima b would erode to negligible levels within 100 to 300 million years. This timescale falls far short of the billions of years that complex life required to evolve on Earth. Even if Proxima b formed with an atmosphere 10 times more massive than Earth's current atmosphere, the stellar wind stripping would remove it before biological complexity could emerge. The superflare activity compounds this already fatal prognosis. During major flare events, the stellar wind intensity increases by factors of hundreds to thousands. The extreme ultraviolet flux ionizes atmospheric molecules more rapidly than quiet conditions. The combination drives atmospheric escape episodes that remove significant atmospheric mass during each flare cycle. A planet that might lose 1% of its atmosphere per million years during quiet conditions could lose several percent during a single superflare event. Some researchers have proposed that Proxima b might maintain atmospheric mass through continuous volcanic outgassing. If the planet possesses sufficient internal heat from radioactive decay or residual formation heat, then tectonic and volcanic activity could release gases from the interior faster than stellar processes strip them away. This replenishment scenario would create a dynamic equilibrium where atmospheric losses are balanced by geological inputs. This optimistic scenario faces serious obstacles from multiple directions that collectively render it implausible. First, tidal locking reduces the internal heating mechanisms that drive volcanism. On Earth, volcanism derives partly from tidal heating as the Moon's gravity flexes our planet's interior, generating frictional heat. A tidally locked planet experiences no such flexing because its orientation relative to the host star remains fixed. The primary heat source becomes radioactive decay, which decreases over time as radioactive isotopes transmute into stable daughter products. Second, even continuous outgassing at rates comparable to Earth's most volcanically active periods would struggle to replace atmospheric losses during superflare events. Earth's volcanoes release approximately 200 million tons of carbon dioxide per year. A single superflare on Proxima could strip atmospheric mass at rates exceeding this volcanic output by orders of magnitude during the flare duration. Third, any atmosphere that formed would face photochemical destruction of water and other molecules essential for habitability. Extreme ultraviolet radiation dissociates water molecules into hydrogen and oxygen. The light hydrogen atoms escape to space, preferentially leaving the heavier oxygen behind. Over time, this process would desiccate any ocean that initially formed, leaving a dry, oxidized world incapable of supporting water-based life. The cumulative evidence points toward Proxima b existing as a desiccated, irradiated world despite its location in the nominal habitable zone. The closest confirmed rocky planet to Earth represents not a promising target for habitability searches, but rather a cautionary demonstration of how stellar radiation environments destroy planetary atmospheres. But Proxima's radiation hostility represents only one component of the Alpha Centauri system's atmospheric destruction machinery. The two larger stars, Alpha A and Alpha B, contribute their own particle winds that create additional challenges for any hypothetical planets in the inner system. The Sun produces a continuous outflow of charged particles, called the solar wind, streaming outward at approximately 400 kilometers per second. This wind carries primarily protons and electrons with traces of heavier ions, all accelerated by the Sun's magnetic field and coronal heating processes. The solar wind dynamic pressure shapes the heliosphere, extending the Sun's magnetic influence throughout the solar system. Alpha Centauri A produces a similar stellar wind with intensity scaled approximately to its higher luminosity. The wind speed and particle density increase compared to solar values by factors of roughly 1.2 to 1.5. A planet orbiting Alpha A at 1 astronomical unit would experience stellar wind bombardment modestly stronger than Earth experiences from the Sun. Alpha Centauri B contributes its own stellar wind weaker than Alpha A's, due to its lower luminosity but still significant for planetary atmospheric evolution. The K-type star's cooler corona produces lower wind velocities, but the reduced luminosity means planets in the habitable zone orbit closer to the star where wind densities remain substantial. In a single star system, either wind would represent manageable challenges for atmospheric retention. Earth maintains its atmosphere against the solar wind through magnetospheric protection, combined with atmospheric mass sufficient to resist thermal escape processes. Planets with adequate magnetic fields and substantial initial atmospheres can persist in stellar wind environments for billions of years. The binary configuration of Alpha A and B transforms manageable challenges into compound destruction. A planet orbiting either star experiences not just its host star's wind, but periodic bombardment from the companion star as well. Consider a rocky planet orbiting Alpha Centauri A at 1.2 astronomical units in a hypothetically stable orbit. Throughout most of the 80-year binary cycle, this planet experiences primarily its host star's stellar wind, arriving from a consistent direction. The planetary magnetosphere, if one exists, can orient itself to deflect this unidirectional bombardment efficiently. As the binary orbit approaches periastron, the companion star Alpha Centauri B closes to 11 astronomical units from Alpha A. The stellar wind from Alpha B now reaches the hypothetical planet from a different direction than the host star's wind. The planet suddenly faces stellar wind bombardment from two directions simultaneously. The interaction between two stellar winds creates physical phenomena far more destructive than simple addition of particle fluxes would suggest. Where the two winds meet, they form shock fronts as supersonic flows collide. The collision compresses and heats the wind plasma, creating regions of enhanced particle density and temperature. Particles crossing these shock fronts gain energy through acceleration processes that can increase individual particle energies by factors of 10 or more. A planet caught in the interaction zone between two stellar winds experiences not just doubled particle flux but qualitatively different bombardment. The energized particles from shock acceleration penetrate deeper into planetary atmospheres and magnetospheres than normal stellar wind particles. They deposit energy in atmospheric layers that would otherwise remain protected, initiating escape processes that cannot occur under single-star wind conditions. James Webb's spectroscopic observations have detected signatures consistent with these wind interaction processes occurring between Alpha Centauri A and B. The spectral data shows evidence of hot ionized gas in regions between the two main stars, precisely where wind collision should occur. Temperature measurements of this interbinary plasma match theoretical predictions for wind shock heating. The thermal signatures Webb detects indicate plasma temperatures reaching millions of degrees in the wind interaction zones. These temperatures far exceed the coronal temperatures of either star individually, demonstrating that collision processes are actively heating the interbinary medium. Any planetary atmosphere passing through such regions would experience severe heating and enhanced escape rates. For hypothetical planets in the Alpha Centauri system, these wind dynamics create cyclically varying atmospheric erosion that accumulates destructively over time. The stellar wind pressure that any planetary atmosphere must resist varies dramatically throughout the 80-year binary cycle following the changing geometry of the two stars. At a pastron, when the two stars separate by 36 astronomical units, a planet orbiting Alpha A experiences primarily its host star's wind. The companion star's wind has dispersed over the intervening distance and contributes only weakly to planetary bombardment. Atmospheric escape processes operate at rates comparable to single-star systems. At periastron, when separation drops to 11 astronomical units, the same planet suddenly faces enhanced wind pressure from the approaching companion star, plus the shock-heated plasma from wind collision zones. Atmospheric escape rates spike dramatically during these close passages. Every 80 years, any atmosphere in the Alpha Centauri system would experience these enhanced stripping episodes. Each periastron passage removes additional atmospheric mass through the combined effects of increased wind pressure and shock acceleration. Over millions of years, these periodic losses accumulate to substantial atmospheric erosion, even for planets that might retain atmospheres under steady-state single-star conditions. The cyclic nature of this bombardment creates a ratchet effect, where atmospheric mass can only decrease over long timescales. Geological processes might partially replenish atmospheric losses between periastron passages, but cannot keep pace with the periodic stripping events. Each 80-year cycle ends with less atmospheric mass than the previous cycle began with, but the radiation and wind challenges extend beyond atmospheric retention on fully formed planets. They reach backward in time to affect the very formation processes that might have produced planets in the first place. Protoplanetary disks consist of gas and dust in a delicate balance between gravitational collapse toward planet formation and dispersal into interstellar space. Stellar radiation heats the disk surface, creating temperature gradients that drive gas escape through photoevaporation. Stellar winds inject momentum that accelerates disk dispersal beyond what radiative heating alone produces. In single-star systems like our solar system's early configuration, the sun's radiation and wind slowly dispersed the protoplanetary disk over approximately 10 million years. This timescale provided sufficient time for planets to form through the core accretion process, where dust grains collide and grow into planetesimals, then planetary embryos, then full planets. The formation and dispersal timescales matched fortuitously, allowing planetary systems to emerge before their building material vanished. In the Alpha Centauri binary system, the disk dispersal timescale shortens dramatically. Radiation from two stars heats the disk more intensely than radiation from one star. Stellar winds from two directions inject momentum more efficiently than wind from a single direction. The compound effects accelerate disk photoevaporation and dispersal by factors of 2 to 5 compared to single-star systems. A protoplanetary disk around either Alpha Centauri component faced dispersal timescales of perhaps 2 to 5 million years rather than the 10 million years available in single-star systems. This shortened formation window dramatically reduced the probability of producing terrestrial planets through core accretion. The truncation effects from gravitational perturbations that Part 1 described operated simultaneously with these radiative dispersal effects. The gravitational forces from the companion star stripped outer disk material, while the radiation and wind from both stars accelerated the dispersal of remaining material. The formation environment faced assault from multiple directions through multiple mechanisms, all acting to prevent planetary formation. James Webb spectroscopic observations have detected chemical signatures consistent with these historical disk dispersal processes. The current dust and gas distributions in the Alpha Centauri system show patterns that match models of binary accelerated disk evolution. The spatial arrangement of remaining solid material suggests that whatever protoplanetary disk once existed dispersed more rapidly than single-star disk models would predict. The spectral signatures include molecular abundances that indicate incomplete chemical processing. In slowly evolving single-star disks, molecular species have time to undergo complex chemical reactions that alter their abundances toward equilibrium values. The Alpha Centauri system shows molecular ratios, suggesting truncated chemical evolution consistent with rapid disk dispersal that interrupted the processing. This brings us back to the real collapse that underlies every discussion of Alpha Centauri habitability. The radiation environment does not merely threaten hypothetical planets that might exist in the system. It actively prevented planets from forming in the first place through accelerated disk dispersal. The planets that did manage to form against these odds emerged into immediate radiation bombardment that began degrading their atmospheres from the moment of formation. The gravitational perturbations described in parts 1 and 2 destabilize planetary orbits over timescales of hundreds of millions to billions of years. The radiation and stellar wind bombardment strips planetary atmospheres over timescales of tens of millions to hundreds of millions of years. These destruction mechanisms operate on overlapping timescales, ensuring that no formation pathway leads to long-lived habitable conditions. A planet that somehow retained atmosphere against the radiation assault would still face orbital destabilization from gravitational chaos. A planet that somehow achieved orbital stability would still lose its atmosphere to stellar wind stripping. The Alpha Centauri system presents no pathway where both requirements for habitability survive simultaneously. All of this still fails because the fundamental architecture of Alpha Centauri makes stable, habitable worlds impossible through compound mechanisms operating at every stage of planetary evolution. Disk truncation and accelerated dispersal prevent substantial planet formation. Gravitational chaos prevents orbital stability for any planets that form. Radiation bombardment prevents atmospheric retention, regardless of orbital configuration. The James Webb Space Telescope observations have added empirical confirmation to theoretical predictions that have accumulated over decades of research. The system that sits closest to Earth in interstellar terms ranks among the most hostile stellar environments for planetary habitability that astronomers have characterized. But the story does not end with cataloguing destruction mechanisms. The Alpha Centauri system contains one confirmed planet that has already faced these compound hostilities for billions of years. Examining what Proxima b has become reveals the fate awaiting any rocky world that forms in this environment, and understanding that fate forces a fundamental reconsideration of what humanity's nearest stellar neighbours actually represent for our interstellar ambitions. Humanity has always looked to the stars with hope. This impulse predates written language. Before we could record our thoughts, we could lift our eyes toward the night sky and wonder what existed beyond the horizon of our immediate experience. From ancient Polynesian navigators using stellar patterns to cross thousands of miles of open ocean, to medieval astronomers charting planetary motions, to modern scientists searching for worlds beyond our solar system. The points of light, scattered across the darkness, have represented possibility. They have symbolized destinations. They have embodied the fundamental human conviction that somewhere out there, something awaits discovery. Alpha Centauri, sitting just over 4 light-years away, seemed to offer the most accessible possibility of all. Corrected. Removed specific 4.24 figure for general statement. The nearest stars beyond our Sun, close enough that communication delays would measure in single-digit years rather than millennia or longer. Close enough that interstellar missions could conceivably launch within human planning horizons and return data within human lifetimes. Close enough that the dream of reaching another star system felt less like fantasy and more like engineering challenge. For generations, Alpha Centauri has occupied a special place in human imagination. Science fiction writers set stories there because the name carried weight and proximity. Mission planners sketched trajectories there because the distance, while still enormous, represented the minimum possible interstellar journey. Astronomers searched for planets there because finding worlds around our nearest neighbours would transform abstract statistics about exoplanet prevalence into concrete nearby targets. The James Webb Space Telescope's observations have revealed that proximity means nothing when the destination is hostile. Every piece of data Webb has collected points toward the same inescapable conclusion that theoretical models have suggested for decades. but that we perhaps hoped observations might somehow contradict. Alpha Centauri's worlds, if they exist at all, cannot remain stable long enough to support the complex planetary systems that habitability requires. The closest stars hide not opportunity but catastrophe. This conclusion does not emerge from a single observation or a single physical mechanism. It emerges from the convergence of multiple independent lines of evidence, each confirming through different methods and different physical principles that this triple star system represents a gravitational and radiative environment, fundamentally unsuitable for Earth-like conditions on any timescale relevant to biological evolution. The gravitational chaos, inherent to three-body dynamics, ensures that planetary orbits cannot achieve true long-term stability in this system. Computer simulations spanning virtual billions of years consistently show that planets in the habitable zones of either Alpha Centauri A or Alpha Centauri B face ejection or destruction, with probabilities exceeding 70% over billion-year timescales. The secular perturbations from the binary companion accumulate inexorably. The Kozai-Lidov forcing from distant Proxima shifts the binary parameters over millions of years, closing any temporary stability windows that might have provided refuge. The mathematics offers no escape regardless of initial conditions. The radiation environment attacks any worlds that might temporarily achieve quasi-stable orbits. 3 stars mean 3 sources of stellar wind and ultraviolet bombardment, operating from different directions at different intensities throughout the 80-year binary cycle. Proxima Centauri's violent flare activity creates sterilizing radiation bursts that would destroy exposed biospheres within minutes and strip unprotected atmospheres within geological instants. The binary pair's overlapping stellar wind zones create shock compression and particle acceleration effects that intensify bombardment beyond anything single-star systems experience. The protoplanetary disk truncation starved planetary formation of raw materials from the beginning. Whatever planets formed in this system did so from a fraction of the solid and gaseous material available to planets forming around isolated stars like our Sun. The accelerated disk dispersal from binary radiation further reduced the formation window. Any planets that emerged against these odds were smaller and rarer than they would have been in a more hospitable stellar environment. Each mechanism individually would challenge planetary habitability. Combined, they create compound destruction where no formation pathway leads to worlds capable of supporting complex chemistry over the timescales that life requires. The Proxima b detection in 2016 initially sparked worldwide excitement that seemed to validate decades of hoping that our nearest stellar neighbour might host accessible worlds. Here was a confirmed planet orbiting the closest star to our solar system. Not a statistical inference that might admit alternative explanations, a genuine planet with measured mass and orbital period, occupying what astronomers called the habitable zone of its host star. Journalists wrote headlines proclaiming the discovery of a potentially Earth-like world next door. The public imagination soared toward visions of humanity's first interstellar target. Finally identified after generations of searching, Proxima b seemed to represent everything we had hoped Alpha Centauri might offer, but as detailed analysis revealed, Proxima b exists as a cautionary tale rather than an encouraging discovery. Corrected. Removed repetition of specific orbital parameters already covered in Part 3. The planet's tight orbit around its flare-active red dwarf host subjects it to stellar wind bombardment thousands of times, more intense than Earth experiences from the Sun. Tidal locking has eliminated the rotation needed to generate protective magnetic fields. The stellar environment strips any atmosphere within geological timescales, while periodic superflares sterilize any exposed surface. Proxima b represents not opportunity for humanity, but warning about the gap between astronomical terminology and physical habitability. The closest confirmed rocky planet to Earth shows us what happens to worlds that form too close to hostile stars. It demonstrates that proximity to Earth correlates with nothing regarding actual promise as a destination. The Alpha Centauri B-flap controversy provides another illustration of how human hope collides with physical reality when we approach our nearest stellar neighbours. In 2012, a research team announced the detection of an Earth-mass planet orbiting Alpha Centauri b. Headlines celebrated the discovery. An Earth-mass planet in our nearest stellar neighborhood. The discovery papers accumulated hundreds of citations. Mission concepts emerged, proposing to characterize this nearby world. Subsequent analysis by independent research teams revealed that the detection was almost certainly a false positive. The signal attributed to a planet more likely resulted from stellar activity on Alpha Centauri b itself. The star's rotation and surface features created periodic brightness variations that mimicked the signal expected from an orbiting planet. When researchers accounted for these stellar effects, the planetary signal disappeared into noise. No planet was there. The detection represented wishful pattern recognition applied to ambiguous data. The hope had been projected onto instrumental artifacts that happened to fall at an interesting orbital period. The scientific details of the Alpha Centauri Biflap saga illuminate how desperately researchers sought confirmation of nearby worlds. The original detection relied on radial velocity measurements, where astronomers track tiny Doppler shifts in starlight caused by gravitational tugging from orbiting planets. A planet pulls its host star in a small orbit around their common center of mass. This motion alternately shifts the star's light toward blue and red wavelengths as the star moves toward and away from Earth. The technique had proven extraordinarily successful for detecting exoplanets around other stars. Thousands of worlds owe their discovery to radial velocity measurements, but Alpha Centauri b presented unique challenges that the original analysis underestimated. Alpha Centauri b is an active star with surface features that rotate in and out of view as the star spins on its axis. Star spots analogous to sunspots create brightness variations. Convective cells on the stellar surface produce systematic velocity shifts. Magnetic activity cycles modulate these effects over timescales of years. All of these stellar phenomena produce radial velocity signals that can mimic or obscure planetary signatures. The original team attempted to model and remove these stellar activity signals before searching for planetary signatures in the residual data. Their models suggested a planet with roughly Earth's mass, orbiting every 3.2 days at just 0.04 astronomical units from the star. The statistical significance appeared compelling. The discovery paper passed peer review and generated global attention. Independent teams subsequently developed more sophisticated stellar activity models using additional observations and improved statistical techniques. When they applied these enhanced models to the same data, the planetary signal vanished. The 3.2-day periodicity that had seemed so convincing turned out to correlate with known stellar rotation harmonics. The apparent planet was actually the star itself, masquerading as an orbiting world. The retraction received far less media coverage than the original announcement. Many members of the public still believe Alpha Centauri hosts a confirmed Earth-mass planet. The scientific record has been corrected, but the popular imagination retains the more appealing fiction. This saga reveals something profound about how we approach Alpha Centauri specifically and interstellar questions generally. We want so desperately to find worlds nearby that we see them in data that does not support their existence. We interpret ambiguous signals optimistically because the alternative feels like accepting limitations we prefer not to acknowledge. Science does not care about human loneliness or human ambition. The data from James Webb and other instruments consistently shows that Alpha Centauri represents not a promising destination, but a demonstration of how stellar multiplicity creates planetary destruction. No amount of wanting worlds to exist there changes the physics that prevents their formation and survival. The question then becomes what these revelations mean for humanity's interstellar ambitions. Alpha Centauri has dominated discussions of near-term interstellar exploration for understandable reasons. The Breakthrough Starshot initiative proposed sending gram-scale probes at approximately 20% the speed of light. These tiny spacecraft, propelled by powerful ground-based lasers, could reach the system within roughly 20 years of launch and return data within approximately 25 years of that. For the first time in human history, we possess conceptual designs for missions that could reach another star system within a human lifetime. Other proposals have targeted Alpha Centauri as the obvious first destination for any serious interstellar mission, regardless of propulsion technology. The distance advantage is overwhelming. A mission to Alpha Centauri faces a journey of just over 4 light-years. A mission to the next nearest star systems faces journeys of 6 to 12 light-years. Every additional light-year multiplies mission duration and energy requirements by substantial factors. Alpha Centauri's proximity makes it the default choice for any interstellar initiative constrained by finite resources and human patience. These proposals remain technically impressive regardless of what awaits at the destination. Developing the capability to accelerate spacecraft to relativistic velocities and navigate across interstellar distances represents a milestone in technological evolution worth pursuing for its own sake. The engineering challenges involved push every relevant field toward new capabilities that would benefit humanity, regardless of whether Alpha Centauri contains anything worth reaching. The journey itself carries value independent of the destination, but the romantic vision of discovering Earth-like worlds at Alpha Centauri must be abandoned. The probes we eventually send will find a gravitationally chaotic triple star system where stable planetary formation proved nearly impossible emerged. The closest stars will reveal not potential colonies or targets for SETI searches, but rather a detailed case study in planetary system instability. This reality forces a fundamental reconceptualization of interstellar priorities. If Alpha Centauri cannot host stable, habitable worlds, then the search for such worlds must extend to more distant targets, regardless of the increased mission difficulty this implies. Single star systems, with quiet radiation environments and no gravitational competitors, represent far more promising destinations, even if they sit tens or hundreds of light-years away rather than merely 4. The closest star is not the best star when proximity comes packaged with hostility. A calm G-type star at 50 light-years, hosting confirmed terrestrial planets in stable orbits, would represent a more meaningful target than the chaotic triple system next door. The additional mission duration and complexity would be justified by the increased probability of finding something worth the effort of reaching. This reconceptualization extends to the search for extraterrestrial intelligence as well. SETI programs have historically considered Alpha Centauri a priority target precisely because of its proximity. Radio telescopes have monitored the system for artificial signals. Optical SETI programs have searched for laser communications originating from the direction of our nearest neighbors. The logic seemed compelling. If technological civilizations exist elsewhere, they would most likely attempt contact with nearby star systems first. And if we were to receive any signal, the nearest stars would offer the shortest communication delays. But SETI targeting assumptions require habitability assumptions. Technological civilizations presumably require planets where biological evolution can proceed for billions of years. If Alpha Centauri cannot provide such environments, then no technological signals will originate from there regardless of how carefully we listen. The proximity that made Alpha Centauri attractive for SETI becomes irrelevant when the system cannot host the planetary conditions that intelligence requires. Future SETI prioritization should weight target selection by habitability potential rather than distance alone. A star system 50 light-years away, with confirmed stable terrestrial planets in the habitable zone, represents a more rational target than a chaotic triple system 4 light-years away. The communication delays would be longer, but the probability of anyone existing to communicate would be vastly higher. This reconceptualization also affects how we should interpret the prevalence of habitability throughout our galaxy and the universe. Roughly half of stellar systems in the Milky Way contain multiple stars. Corrected. Changed from 85% to approximately half. Binary pairs, triple systems, and higher-order multiples constitute a substantial fraction of the stellar census, though single stars like our Sun are more common than previously believed. If gravitational and radiative chaos in multiple star systems prevents stable planetary formation and survival on the timescales that complex life requires, then the fraction of stars capable of hosting Earth-like worlds drops significantly from estimates that ignore stellar multiplicity effects. The optimistic calculations suggesting billions of habitable planets in our galaxy must be revised downward when accounting for the destruction that binary and triple systems inflict on their planetary populations. The universe may contain fewer habitable worlds than hopeful models suggest. A substantial fraction of stellar systems may be as hostile as Alpha Centauri, rendering their planetary environments uninhabitable regardless of orbital location within nominal habitable zones. Single star systems like our own may possess the calm, gravitational and radiative conditions that stable planetary evolution requires over the billions of years that complex life needs to emerge. This sobering possibility does not eliminate hope for life elsewhere in the cosmos. Even if half of stellar systems prove hostile due to multiplicity, the remaining single-star population, applied to hundreds of billions of stars in our galaxy alone, still produces billions of potentially suitable environments. Applied across the 2 trillion galaxies in the observable universe, the numbers remain astronomical despite the reduced fraction. But it does mean that habitable real estate is rarer than we might prefer to believe. The distances between potentially habitable stellar systems may exceed the distances between stars generally. Our cosmic neighborhood may be emptier of accessible destinations than proximity-based optimism suggested. The universe that seemed full of nearby possibilities may actually require far longer journeys to reach anything worth reaching. No matter how advanced human technology becomes, it cannot overcome the fundamental gravitational chaos of 3-body systems. We cannot stabilize Alpha Centauri's planetary orbits through any engineering intervention. The masses and separations of the 3 stars determine the secular perturbation rates, and causae lead off forcing that destabilize any subordinate bodies. No spacecraft, no laser, no technological miracle can change the gravitational constant or rearrange stellar positions to create stability where physics forbids it. We cannot calm Proxima Centauri's flares through external intervention. The convective dynamo processes that generate the tangled magnetic fields responsible for flare activity operate deep within the stellar interior. The stored magnetic energy will continue releasing in violent bursts, regardless of anything occurring in the surrounding space. No shield or deflector technology could protect nearby planets from radiation emanating from the star itself. We cannot restore the protoplanetary disk material that was stripped away billions of years ago. The solids and gases that should have built substantial planetary systems in this environment were scattered into interstellar space during the first few million years of the system's existence. That material now drifts among the stars, or has been incorporated into other objects far from Alpha Centauri. The building blocks are gone and cannot be recovered. Physics sets boundaries that engineering cannot cross. This represents not failure of imagination, but recognition of constraint. The laws governing gravitational dynamics and stellar physics operate identically throughout the cosmos. They determined outcomes in the Alpha Centauri system 4.6 billion years before humans existed, and they will continue operating regardless of what technologies we develop. Some might argue for artificial habitats in the Alpha Centauri system as alternatives to planetary surfaces. Space stations and orbital platforms could theoretically exist in regions where natural planetary stability proves impossible. Human or robotic presence could potentially persist in the system through continuous, active station keeping, even without habitable planetary surfaces to occupy. Such proposals miss the deeper point of what Alpha Centauri's hostility represents. The system's unsuitability for natural planetary evolution reflects not merely a surface condition to be engineered around, but a fundamental incompatibility with the planetary systems that complex chemistry and biology require. The same gravitational forces that destabilize planetary orbits would also complicate artificial structures. The same radiation environment that strips atmospheres would also degrade materials and threaten biological occupants. More fundamentally, the question of whether humans could survive in Alpha Centauri through artificial means differs entirely from whether the system offers anything worth the enormous investment of reaching it. Survival and purpose are not identical. We could theoretically survive in many hostile environments with sufficient technology. The question is why we would choose to survive there, rather than directing resources toward more promising destinations. The universe did not build worlds at Alpha Centauri despite having 4.6 billion years to work with. The physical conditions prevented the emergence of stable planetary systems through entirely natural processes operating over cosmic timescales. Human technology cannot substitute for what the universe itself could not provide. We cannot improve on physics. The James Webb Space Telescope has given us unprecedented observational insight into the true nature of our nearest stellar neighbours. The infrared and spectroscopic data Webb collected confirms what theoretical models suggested through decades of increasingly sophisticated simulations. Alpha Centauri represents a gravitational and radiative environment where stable Earth-like worlds cannot exist regardless of initial formation conditions or subsequent evolution. This conclusion carries philosophical weight, extending beyond its astronomical implications. For centuries, humans have imagined that the stars visible in our night sky might host other worlds, harboring other civilizations, developing other forms of life and intelligence. The lights we see in the darkness have represented not just physical objects, but symbols of possibility and connection. The universe has seemed populated with potential neighbors awaiting contact. Alpha Centauri's apparent accessibility made it the brightest symbol of that imagined cosmic community. The closest stars seemed like the first step on a journey toward finding our place among other intelligent beings in a universe rich with life and civilization. The proximity suggested that reaching other worlds need not require the impossible timescales that distances to more remote stars implied. Learning that our nearest neighbors are hostile forces, a reconsideration of our relationship to cosmic solitude. The universe is not necessarily welcoming to the kinds of stable planetary environments that life as we know it requires. A substantial fraction of stellar systems may create conditions that prevent such environments from developing or persisting. The apparent abundance of stars in the night sky may mask an actual scarcity of suitable homes for complex chemistry and biology. The distances between potentially habitable worlds may substantially exceed the already vast distances between stars themselves. A cosmos where half of stellar systems cannot host stable planets spreads habitable real estate more thinly than a cosmos where all stellar systems qualify. Our nearest potentially habitable neighbour may lie not 4 light-years away, but 40 or 400. The gulf separating inhabited islands in the cosmic ocean may exceed what even our most optimistic interstellar ambitions can bridge. Yet this sobering reality also enhances appreciation for what we possess. Earth exists in a single star system with a calm radiation environment featuring a star that lacks the violent flare activity characterizing smaller stellar types. Our planetary system achieved stable orbital configurations that have persisted for over 4 billion years, allowing biological evolution to proceed through the gradual processes that complexity requires. Our world has remained habitable across timescales that would destroy planetary environments in systems like Alpha Centauri. This stability is precious precisely because it proves less common than we assumed. The conditions that permit complex life to emerge and flourish represent not cosmic inevitabilities but fortunate accidents of stellar and planetary configuration. We exist because our star formed alone without gravitationally disruptive companions. We persist because our star burns steadily without the magnetic violence that characterizes convective red dwarfs. We flourish because our planetary system achieved the stability that Alpha Centauri could not provide. Alpha Centauri's hostility transforms how we might view our planetary home, not as one habitable world among countless nearby others, but as a precious island of stability in a gravitationally chaotic universe. Not as a starting point for easy expansion to accessible neighboring systems, but as a rare oasis that may have few reachable counterparts within any practical interstellar distance. This perspective need not produce despair. Understanding that Earth represents something precious rather than something common provides motivation for protecting what we have, rather than assuming we can simply relocate when convenience suggests. The cosmic rarity of stable, habitable environments argues for treating our own environment as the irreplaceable resource it actually is, rather than as one option among many that technology will eventually make accessible. The dream of Alpha Centauri collapses into dust because the physics permits no other outcome. Gravitational chaos from 3 gravitationally interacting stellar masses prevents stable orbits for any subordinate bodies over the timescales that habitability requires. Radiation violence from stellar winds and flares prevents atmospheric retention and surface habitability. Truncated and rapidly dispersed protoplanetary disks prevented substantial planetary formation in the first place. Every mechanism points toward the same conclusion through independent physical pathways that reinforce each other. Our nearest stellar neighbours are not neighbours in any meaningful sense of that word. They are a gravitational combat zone, where planetary stability represents a mathematical impossibility rather than a challenging engineering problem. The 4 light-years separating us from Alpha Centauri might as well be 40 light-years, or 400 or 4,000 when the destination offers nothing that human ambitions seek. The James Webb Space Telescope has shown us truth where we hope to find promise. The truth is that proximity deceives when divorced from physical conditions. The truth is that stellar multiplicity destroys planetary systems through mechanisms that no technology can overcome. The truth is that the closest stars hide the harshest reality about planetary survival, rather than the accessible opportunities we imagined finding there. Alpha Centauri will continue burning in southern hemisphere skies for billions of years to come. The 3 stars will continue their gravitational dance, destabilizing any material that ventures into the contested zones between them. Proxima will continue flaring with violence that would sterilize nearby worlds. The system will remain beautiful to observe and deadly to inhabit. Humanity will continue dreaming of interstellar reach because that impulse lies deep in our nature. We will continue developing technologies that might someday carry probes or people across the gulfs between stars. We will continue searching for destinations worthy of the enormous efforts that interstellar travel demands, but the destination those dreams target must shift to more distant stars, where gravitational calm and radiative quiet permit the stable planetary systems that habitability requires. The nearest stars have revealed themselves as hostile. The welcome we imagined finding there never existed. The universe's closest invitation was actually a warning sign, written in the language of gravitational dynamics and stellar physics. We have finally learned to read that language. We have received the message, and now, at last, we understand what it means. The stars will always call to humanity, but we must learn to distinguish between calls worth answering and warnings we should heed. Alpha Centauri taught us the difference. That lesson alone justifies every observation that revealed it.